Hi guys, welcome to Unit 56. In this unit, we're going to talk mainly about the temperature, the surface temperature of the stars, that is, and the star's composition. And we'll see that there is a correlation actually between how the temperature is and basically how high is the temperature and what is and what is not ionized on the surface of the star. So basically, we're going to explain why stars have spectral lines, and that's because of the elements that exist in their atmosphere, basically. Describe how spectral lines were developed and list their temperature order. Okay, the how should I say it? Depending on how much temperature, energy levels in the star can be excited, okay, or in the gas that is surrounding the star can be excited. And some of the gas actually, like helium, hydrogen, for example, can be ionized. So in this case, we really have to get into another element, which is helium in this case. Okay. So explain the basic principle of Venus law that we saw in a different unit way back. Okay. And there is a correlation between the temperature of an object and the maximum or the peak frequency or the peak wavelength that is emitted. The hotter the object is, the the shorter the wavelength, the higher the frequency, basically. Okay. And then we're going to talk about the spectral lines and classifications and things like that. Again, the star, or at least the journey of a photon from inside the core of the star all the way to its surface, takes a long time. But when it does, it's going to go through the atmosphere of the star, or at least the gases that exist immediately above the photosphere of that star. One of these gases is hydrogen. Hydrogen has well-known spectral lines. We know exactly what emissions hydrogen does. If any transition involves the lower level, the ground state of the hydrogen, that is actually ultraviolet radiation. We cannot see it with the naked eye. Anything that involves the first excited state, which is the second level, and higher levels is something that we can see. If it is a short transition, we're talking about, or this transition, for example, from higher levels is actually very short also, that involves long wavelength. In this case, it's going to be an infrared. Actually, we're not going to be able to see it. Involving level 2, then we're going to see the immediate transition, which is actually short energy, less energy, I shouldn't say short. It's less energy. Then in this case, it's long wavelength. So in this case, it's going to be red. Then you have the blue, which involves the next one. And then you have actually two lines in here in the violet region. Okay. So there is the UV region, which involves a lower level and any higher level, not just level 2. And then the second level is the visible region. That's light that we can see between the second and the third, second and the third, the fourth, I'm sorry, the second and the fifth, and so on. Then after that, the level starts to collapse on one another. As a matter of fact, between the next level and the levels above that, they are going to be in the infrared. There will be very little energy, very long wavelength. We can't see either. Okay. So if we run this through a spectrometer, basically the light that is coming from the star, for example, for the case of, we're going to see this telltale signs that hydrogen exists actually as an atom on the surface of the star, okay, because it has this spectral lines. Albeit I said in here there is a faint one in this side, okay? But that's signature of the hydrogen because these lines have a definite values that we can compare them to the lab if the star is not moving. Okay? If the star is moving, we can just find the shift from where they were and find actually how fast the star is moving. Okay. So from level 2 to 3, from 2 to 4, from 2 to 5, those are the ones that we can see. Anything on the other side, which is the UV region, or on this side, which is the infrared region, we're not going to be able to see with the naked eye at least. We have to have fancy equipment to find it. So that's basically the spectrum. This is called an absorption spectrum because light is missing from the spectrum. If I look with the naked eye to Orion, for example, we see Betelgeuse on this side appears reddish in color, whereas Rigel appears blue on the opposite side of Orion. But if I run it really through a spectrometer, the peak wavelength is not exactly at the red for the case of Betelgeuse, but it's actually in the infrared, around 900 Kelvin. 900 nanometers, I'm sorry. The x-axis in here is in nanometers, and the y-axis in here is the intensity, or how bright that light is. So the peak, where it's the brightest, it's around something that is actually in the infrared region. But because we can see this entire thing, our eyes will detect just the red part and start to dim as you move in the color spectrum. For example, for the blue, it's super faint compared to the red. That's why the star appears red. Whereas, for example, Rigel is also peaking also in the ultraviolet, meaning that the peak frequency, we cannot see it, but the first light we're going to see is going to be in the bluish color. That's why it appears bluish. And then the red version of it is very, very faint. So stars that are on one side of the spectrum are peaking because they are super hot. Again, this is Wien's law that we saw before. The temperature in Kelvin, the wavelength, the max wavelength, the peak wavelength is going to be in nanometers. And if we use this formula, we're going to find, basically, this is an experimental law, we're going to find how hot the surface is that gave us that light. This is a much up-close picture to the same phenomenon I was talking about. Actually, if you look at the different stars that constitutes, this is safe, these are the belt in here, this is Bellatrix. They are different shades of actually blue depending on how bright they are. Some of them are actually a little less blue because actually they have less surface temperature than this one. If you extend this belt and go all the way to a region that you can see in here, there is actually another reddish star, which is called Aldebaran, which is part of another constellation. But again, just by visually looking at the stars, you can roughly tell how hot their surface is, just thanks to Wien's law, which is the experimental law, as I said. Actually, there is a theory behind it, but the values in here are based on experiment. Now, if we run a spectrometer, by the way, for those sitting in the lab version of this class, you will see this analysis for some of the labs, basically. If you have the spectrum of the star, you're going to find exactly what is dipping, what the lights, the frequencies, the wavelengths that are missing in this case, based on the analysis that you have, what type of lines are missing, we're going to classify the stars. From the hottest one that we can think of, O, to the coolest one, which is M. Granted that there are newer classifications in here, Y, but the famous ones, or at least the classical ones, are O, B, A, F, G, K, M. And each class tells you the temperature because it tells you exactly what element are we talking about in this case in the spectrum. One way to remember that, at least, is these are some mnemonics. O, be a fine girl, or guy, kiss me, or in here, I don't remember that. I remember just the first one in here. Anyway, it says only bad astronomers forget generally known mnemonics, and that's O all the way to M. So to further refine these measurements, for example, the O extends from about 10,000 Kelvin all the way to 30,000. I mean, O is higher than 30,000 Kelvin. It's actually it's the B, the one that goes next. Okay, so in order to divide that into smaller, finer divisions, we use numbers from 0 to 9. 0 being the hottest, 9 being the coolest, closer to the next lower level, basically. Okay. The Sun, for example, is a G2 type star because it's between 5,000 and 6,000, but it's actually 5,800 Kelvin, closer to the 6,000 by about 2 degrees. So that's why it's a G2 type star versus, for example, a G9, for example, which is closer to 5,000 Kelvin. Here is what I was talking about. Depending on the Balmer lines, basically, for the hydrogen, if it is a hydrogen, depending on the temperature in here, for example, for the O classification in here, there is mainly, in this case, helium in the spectrum because the temperature is too hot for the hydrogen to exist in an atom form, or at least a neutral form. it exists ionized, so you're not going to see it excited. It's not going to absorb any of the radiation. So helium now can exist, at least in some sort of atomic structure that can give you those spectral lines. And you go on all the way throughout, and you're going to pick up more and more elements. So hydrogen now starts to appear for other elements, and then calcium for other elements, for lower and lower temperatures in this case, and more gases exist in the atmosphere that can collect, all the way to basically cool enough that even dust starts to form for the newer classifications. Okay. So here is more about this classification. So the O stars are above 30,000. So ionized helium, weak hydrogen. This is even helium is not in neutral form actually. And then B classification stands between 10 to 30,000 Kelvin. That's a huge range. Okay, compared, for example, for the A classification, which is only about 2,500 Kelvin, between 7,500 all the way to 10,000, and even that is actually a lot, 2,500 Kelvin compared to the next classification, which is 6,000, 7,500, and that's where the sun is. So ionized calcium, strong, and hydrogen, weak, and that's basically the different lines that are showing in those classifications. Up to M, which is between 2,000 and 3,500 classification, that's where Betelgeuse is actually, okay? Including titanium in oxide format, because the temperature is so cool that molecules start to form now. Now, if you go further, there are stars that can allow all the way to basically ammonia and other dust basically starts to form around them. And those are the new classifications, LTY. Thank you.